So our next topic we're getting into is magnetism. Contrary to popular belief, magnetism is not due to a separation of charge. So if you have a permanent magnet, which this is, we talk about one end being the north pole of the magnet and one end being the south pole of the magnet. That doesn't mean one end has excess protons and one end has excess electrons. This thing's neutral. The protons and electrons are uniformly spread throughout the entire magnet. Magnetism in a permanent magnet is due to what's called magnetic domains. When you have a piece of iron, for example, if it's not magnetized, it has a whole bunch of little magnetic domains that are randomly oriented throughout the magnet. If you place this piece of iron near a permanent magnet, those little domains turn and line up with each other. They line up with that external magnet's field. And create a net magnetic, what we call a dipole moment within the magnet. Magnetic dipole moment points throughout the entire magnet. It's actually an extension of the magnetic field that the magnet creates. The symbol we use for the magnetic dipole moment is a mu, a lowercase mu. It is a vector. It does have a direction associated with it. Within a magnet, the magnetic dipole moment points from the south end of the magnet towards the north end of the magnet. So similar to electricity, when we talked about electric field, how the charges can influence the space around them, with magnets we talk about what's called the magnetic field. And it's how two magnets interact with each other without physically touching. Something interesting about the magnetic field, it's a continuation of this magnetic dipole moment. So magnetic fields, if we're looking outside the magnet, they point away from the north magnetic pole. They wrap around and come back in at the south magnetic pole. Magnetic fields are continuous. They don't start anywhere and stop anywhere. There's no starting and no stopping. It's a continuous loop. The symbol we use for magnetic field, I'm not sure who came up with it, but it's a capital B. So capital B is used to represent the magnetic field, which is the field outside of our magnet. The units we use are called Teslas. We use a capital T to represent it. For example, Earth's magnetic field. Earth has a magnetic field. Earth's magnetic field is on the microtesla scale. It's pretty small. It's actually unusual to get something close to 1 or 2 Teslas. They have done it with electromagnets, where you have a piece of iron as well as a coil of wire. So, for example, in MRI machines in the hospitals, they're around 1 or 2 at this point, 1 or 2 Teslas. Okay, so magnetic fields point out of north poles into south poles, and inside the magnet they continue on south to north. So they don't start and stop anywhere. I have a little demonstration for you. This is a bunch of iron filings, and they're suspended in some type of oil in here. Iron is what we call a ferromagnetic material. It's very easily magnetized if it's placed in a region where there's a magnetic field. So if I take my magnet and I slide it in there, those little iron filings are going to line up with that magnetic field that's created by my bar magnet. So this kind of gives you a visual representation of what the field looks like. Pass it around so you can play with it. Shake it up really good. Now it turns out electricity and magnetism are very intimately related. It's really difficult to find one without the other. But I have here a little wire. This wire, I'm not sure if it's aluminum or what, but it is not a magnetic material. It's not ferromagnetic, meaning it's not easily, it's not magnetized if it's brought near a magnet. Any material that's easily magnetized when it's brought near a magnet is called a ferromagnetic material. This magnet's not strong enough. There we go. So my Leatherman, for example, it's made of ferromagnetic material. In and of itself, it's not normally magnetized. It's not normally a magnet. But when I use another magnet and bring it close by, that allows those little domains to line up, and the Leatherman acts as if it's a little magnet itself. It won't stay magnetized. This piece of wire that I have here is not ferromagnetic. Oh, magnet is. But if I take my magnet here and bring it close to this wire, it doesn't do anything. It can't attract it or repel it. So the wire itself is not ferromagnetic. I'm not sure what it's made of. Whatever it's made of, it's not capable of becoming magnetized just by bringing a magnet close. This guy's a magnet. There's actually two of them here. I'm not sure which end's the North Pole and which end's the South Pole, but the magnetic field between those two magnets is either pointing that way or that way. It's pointing from one of the magnets to the other. So I'm setting it up so that I can swing that little piece of wire between my magnet here. Make sure it doesn't run into it. There was a scientist named Oersted, I'm not sure what period of time, it was probably 1800s sometime or early 1900s. He taught physics, and he was just dead set on teaching his students that there was no relationship between electricity and magnetism. It's just, once and for all, I'm going to get this out of the way. And he brought in a wire and a big battery and a compass needle. Now compass needles are just little teeny tiny magnets. And when you have a compass needle in a magnetic field, that little needle lines up with the magnetic field. So he's going to prove that that compass needle didn't move anywhere around that wire. Interestingly enough, instead of proving there was no relationship between the two, he proved there was. If you flow current through a wire, it now is suddenly interacting with that magnetic field. So it is the motion. Magnetic fields are due to the motion of charges. Charges that are moving. Any charge that moves creates a magnetic field. So my battery is causing the electrons to move through this wire, where it's getting offset because of the magnetic force that's pushing it to the side. If I switch the polarity, make current flow the other way, gives it enough energy this time. But the net force is in the opposite direction when I switch the direction of the current. So this piece of wire is not ferromagnetic, meaning it cannot be magnetized by just holding it near a permanent magnet. But if I flow current through it, then it does have magnetic properties, and those magnetic properties, it creates a magnetic field which then interacts with the magnetic field of the bar magnet there. So the fundamental cause of magnetism, as we understand it, is the motion of charges. Charges that are moving somehow. So that brings us back to a bar magnet. Currently, it's believed that the motion in here is actually the spin of the electrons. If you've taken chemistry, you've talked about spin as one of the properties of an electron. So they believe it's actually the spin of the electrons that cause those little domains, and they're normally just randomly oriented. When you create a permanent bar magnet, it aligns all those little spins up and creates a permanent magnet.
Is that a theory or is that been proven?
I'm not sure if they've proved it directly, so I believe it's the current understanding of it, but I don't know that they've actually proven it experimentally. So the Earth has a magnetic field. We're actually very lucky it has a magnetic field, because the sun is continually emitting not only light, but it's emitting charged particles all the time. So all these billions of charged particles are flowing through space. Well, charged particles with our satellite systems, for example, or our power grids, cause some serious problems. There have been periods of time, actually, when we've lost contact with some of the satellites because of high, what we call solar winds. And so what usually happens with the Earth's magnetic field, so here's Earth, here's the north geographic pole and the south geographic pole, so Santa and the penguins. Currently, the Earth's magnetic field is coming out down here, wrapping around and coming in back up here, which means it's continuing onwards this way. So magnetically, the north magnetic pole is down here near the south geographic pole. The south magnetic pole is up here near the north geographic pole. What happens is those charges that are coming from the sun, well, since they're moving charges, they have their own little magnetic field, and when they get to the magnetic field of the Earth, they actually interact. And most of them actually end up trapped. They start circling around the magnetic field lines. They get trapped because of the forces and the interactions with this external magnetic field, which is good for us. Now, some of them, depending upon how we're oriented relative to the sun, some of them can come in down towards the south magnetic pole. It turns out, if the charge is moving in the same direction, so if I have a little charge moving in the same direction as the field of the Earth, nothing will happen to it. At least no magnetic forces will occur with it. Okay? And so those charges actually come in and they hit the atmosphere, hence the northern lights. Same thing happens in the South Pole region. You get the southern lights. And that's all that is the charged particles ionizing the gas in the atmosphere. Sometimes the sun is a lot more active than other times, so I've actually seen the northern lights here before. It was pretty darn cool. It was totally accidental. I had taken my dog outside for the night, and it's like, wow, the sky looks really weird.
How long ago was that?
It's been a number of years. I can't remember exactly how many years.
They say by 2012 it's supposed to be a huge solar storm.
It could be.
I think a couple months ago they saw the first of that.
I know it's, yeah, the activity's getting pretty big right now. It was at least 6 years ago that I saw it, because it was before I moved. So the Earth's magnetic field, the current theory, because we believe magnetism is completely dependent on moving charges, the Earth has a partially molten core, and the Earth rotates on its axis, So they believe that's the source of the magnetic field, is that moving charges. But they've got some questions to answer. Turns out Earth's magnetic field changes in orientation with time. It doesn't stay in the same place. In fact, there's evidence, geological evidence, that it's flip-flopped in the past.
Ooh, no shit.
So they have yet to be able to describe why that happens. So we don't know. We don't know why.
It's dangerous whenever it happens, though. That's for sure.
Hopefully it just would flip-flop. The direction of it wouldn't matter to us. The disappearing of it would matter to us. So if it just flip-flopped without actually disappearing, we'd be fine.